to introduce you to Farima. Farima is a final year PhD candidate at the University of Michigan, working with Professor Jagadish and Professor Lu Wang. Her research is in NLP, mostly focusing on advancing responsible AI, developing evaluation, and enhancing language models' factuality through novel evaluation methods and intervention techniques. And so without further ado, I will please take it away.
Sure. Hi, everyone. My name is Farima Fatai Bayat, and I'm the final year PhD candidate at the University of Michigan. And I'm very honored to have the opportunity to talk about my research on evaluating and enhancing language model factuality. So before I go into this talk, I wanted to say that I can pause between chapters for quick questions, but more general and high-level questions are preferred to be asked at the end of the talk in the interest of the time. Okay. So today, we live in the age of AI systems that can accomplish many tasks by using language models at their core. And language models are transformer-based parametric models that are widely used for knowledge-intensive tasks. But how do these language models work? Language models are machine learning models that are trained to predict the next token. So during training, a language model has access to a large-scale training corpus, and given a prefix, it's trained to assign the highest probability to the correct token. And at inference time, the model does not have access to the training data anymore, and we hope that it can encode and memorize the knowledge in its own parameters. Language models have shown to be quite effective in many knowledge-intensive tasks. As you can see in this example, ChatGPT has performed well on various scientific exams, such as AP and SAT. However, these models have a tendency to hallucinate, and hallucination is the generation of incorrect or unverifiable statements in language models' output. So, for example, when I ask ChatGPT to tell me about the Olmo team at AI2, it makes many mistakes in predicting the official announcement date, the key leaders, and their roles. And hallucination can lead to serious circumstances, including legal issues, economic losses, and reputational damage. For example, a few days back, a judge fined 3 lawyers for citing hallucinated cases in a court filing. Also, in 2024, Air Canada faced high costs after using a chatbot that invented return policies and had to terminate its chatbot support. Also, language model hallucinations have led to social defamation by falsely accusing public figures of crimes like sexual harassment and vandalism. So at this point, we all agree that hallucination is a serious risk of language models that needs to be controlled. But how can we mitigate this risk? First, let's look at the definition of hallucination to understand it better. So hallucinations are traditionally defined as language model generations not grounded in certain sources. In this example, given a context and the question of when was the first Ebola vaccine approved, the model fails to correct data from its input context, and this is one instance of intrinsic hallucination. Also, if the model generates information that is not part of the context, and so it cannot be verified, this is an example of extrinsic hallucination. And this definition can be naturally extended to the factuality problem or factual inaccuracy, where the model fails to generate statements grounded in world knowledge. So for the same example, for the same question, now in the closed book setting, the model can either produce a wrong answer and a wrong approval date, as you can see in this example, or generate a statement that is not verifiable based on existing evidence. So as you can see in this example, the model believes that the first Ebola vaccine was the greatest breakthrough of the 21st century, which is rather subjective and not established fact. So factuality is language models' capability to generate content that is consistent with the world knowledge. And of course, higher factuality is always preferred. And throughout this talk, I use hallucination and factual inaccuracy interchangeably to refer to cases where a model generates information that is not supported by factual evidence. Okay, so to improve factuality, we first need to understand the challenges that models face in factual generation. And for that, we need to evaluate these models. However, there are limitations in current evaluation benchmarks and metrics. First, there is no systematic approach for identifying scenarios that the model struggles to produce a factual answer. Also, language models engage users in dialogue, engage with users in dialogue and generate long responses. However, evaluating the factuality of long-form text is challenging, and we will see why. After understanding the failures of language models, a key question is, can we guide these models towards factuality without further training? And there are multiple classes of techniques used for inference time improvement. One is prompt engineering techniques that guide models to identify and correct their own mistakes by using prompting techniques such as chain of thought or self-reflection. Also, model ensemble, which enables multiple instances of the same model to debate and refine their answers, can mitigate hallucinations. And finally, manipulating the model's internal representations or output probabilities can offer stronger control and steer models towards factuality. But despite these improvements, can we trust language model generations? And the answer is no, because language models have fundamental limitations. Their knowledge can be outdated, overwritten, biased, or even non-existent. So to address these challenges, a class of techniques called retrieval augmented generations have been introduced to retrieve evidence from external sources and integrate them into the model's generation process. However, these techniques still rely on the model's response, on the language model to generate an output, which means that it can still produce errors or rely on its internal knowledge instead of using retrieved information. And so this is why we need a post-processing tool that can verify factual claims in language model outputs, attribute them to credible sources, and make edits for incorrect claims. And such a tool can further increase the reliability and trust in language model generations. Okay, so here is a roadmap of my today's talk. I start by introducing a factuality evaluation framework, then move to an inference time intervention technique for hallucination mitigation, and finally, a post-processing tool for verification and correction of language model-generated outputs. And the whole goal of the talk is to understand and improve the factuality of language models. Okay, so first I'll introduce a factuality evaluation framework that identifies real-world scenarios where models make factual mistakes, along with a factuality evaluation method that's designed to detect hallucinations in conversational settings. Next, I'll present an uncertainty-aware intervention framework that adjusts interventions based on the input context and enables models to refuse responding when uncertain. And finally, I'll go through a post-hoc verification and correction tool that helps users assess and improve the factual accuracy of model responses. Okay, so first let's go through the factuality challenges in language models. So to understand these challenges, we need an evaluation framework that has prompts that can effectively trigger language models to hallucinate, and a reliable evaluation method that can detect these hallucinations in language models in response to these prompts. So Since language models engage with users through long-form responses, we need benchmarks that assess the factuality of these models in long-form generation. Here is a list of existing benchmarks for evaluating long-form factuality, but they come with major limitations. First, these benchmarks are either human-curated or model-generated rather than being from real-world language model interactions. So in this case, they can fail to capture scenarios that models make mistakes while they're being used in the wild. A fact-check bench, which is a mix of human-generated prompts and a few dozen user prompts where ChatGPT makes mistakes, is insufficient for evaluating the factuality across all models. Second, these benchmarks are static and they are at the risk of data contamination. And this will limit their ability to evaluate new models on evolving real-world scenarios. And finally, the topics and the sample sizes for each topic are determined by the authors, and there is no emphasis on the diversity of the topics. So these limitations motivated me to create an updatable benchmark that challenges language models across diverse and real-world scenarios. But how to build this benchmark? So I explored LMC's Chat 1 million and Wild Chat that are both rich sources of user model interactions and are designed to be periodically updated. I focused on LMC's Chat 1 million for data collection since it contains responses from a more diverse set of models. But to expand our understanding of challenging prompts, we plan to incorporate Wild Chat for the next versions. So we start by collecting the first term of English prompts from the LMC's Chat 1 million dataset and do further cleaning by removing non-English duplicated or anonymized prompts. Then we use a topic modeling technique to cluster prompts into various topics. And this is done to ensure a diverse selection of prompts across different topics. Next, we observe that not all prompts enable verification from language models. So for example, as you can see in here, storytelling and role-playing does not rely on factual knowledge, and also the boundary between a fact and imagination in these scenarios is often blurred. So I classified prompts based on the verifiability of their responses to distinguish between those that require factual grounding and those that do not. And here are top 5 clusters and the proportion of verifiable prompts within each cluster. So as you can see, LM responses to travel planning or company introduction requests require factual knowledge, whereas storytelling does not. And finally, we filter prompts based on their interestingness to avoid including prompts that are niche, like who discovered Kerguelen Islands, or require more context, like what's the size of this room, or are time sensitive. And you can refer to our paper for the criteria and method used to assign a usefulness score to each prompt. So now we have a set of cleaned and verifiable and useful prompts across diverse topics. But how to identify the challenging prompts? So we need to study the model behavior, and to do that, we need to evaluate model response. And how? We do this by quantifying the hallucination degree in the model's output. So factuality evaluation methods in general fall into 2 categories. The first category include reference-free methods, which rely on the probability-based measures or self-consistency checks to assess the factuality of the response without external references. So in this example, the model generates multiple response samples and determines their correctness using aggregation methods such as majority voting. But these methods require multiple calls to the language model and are bounded by the model's knowledge recallability. So the second category, which provides a more reliable assessment of language models, evaluates language models against verifiable knowledge sources such as Wikipedia, web articles, books, or knowledge graphs. So in this example, the LM-generated response is first decomposed into atomic standalone units and then verified against Wikipedia articles to evaluate the factuality. But the problem with the current reference-dependent evaluation metrics is that they cannot effectively handle conversational text, and they make binary decisions, which means that they label each language model statement as either factual or not factual, which means that they fail to distinguish between statements for which there is a contradicting evidence and statements for which no evidence has been found. So to address these issues, I introduced Verify. And Verify performs fine-grained factual annotation for conversational text. And here is an example. For a user request, what are the best solutions to test prompts with LLM models? And a language model response that is included in the LMSys Chat 1 million data, we designed this pipeline to measure the hallucination degree of the model's response. So first, we decompose the language model response into content units and label them based on their verifiability to filter out questions, disclaimers, or other non-verifiable components. Then a unit decontextualization is applied to add necessary context to each unit and makes it standalone and self-contained. Next, I use a query refinement technique that iteratively generates a question for each unit, retrieves search results, and refines the question accordingly to maximize the retrieval of relevant results. And finally, each unit, along with the questions and the web results from the previous step, are sent to this final judgment component to determine their factuality. And each unit is labeled as supported if evidence confirms its accuracy, unsupported if evidence contradicts it, or undecidable if there is no conclusive evidence found. And in this example, the last unit is labeled undecidable because the specific version of the llama model is required to decide on the input format it supports. After having the fine-grained annotation results for the response units, we need a way to measure the hallucination degree of the response. So the hallucination score is computed using the formula you can see here. The denominator is a weighted combination of unsupported, of the number of unsupported and undecidable units. And it's normalized by the square root of the number of verifiable units in the model's response. The lower weight that is assigned to undecidable units is to account for verified potential failure in correctly extracting units or retrieving evidence to assess their factuality. And also the denominator grows sublinearly with the number of verifiable units to keep the score sensitive to errors even in lengthy responses. So now we have a hallucination score that measures the hallucination degree of the model's response. We also consider the responding language model's general performance based on its ranking on Chatbot Arena website to categorize our benchmark into hard, moderate, and easy tiers. And this is due to the fact that weaker language models are prone to hallucination, and so this categorization can help prevent the benchmark from being dominated by prompts and weaker models. And finally, we use the hallucination score of the model's response, the responding model's overall performance, and the prompt's usefulness score from the prompt collection phase to decide on the appropriateness of the prompt for its inclusion in our baseline benchmark. And here you can see our benchmark which is called FactBench, and is a benchmark of 1,000 prompts categorized into easy, moderate, and hard prompts. And the number of prompts in each tier and the models for which these responses have been collected and verified are shown in this table. As you can see, the majority of prompts fall into the hard tier, followed by moderate and easy ones. And this reflects our focus on challenging real-world scenarios where models are more likely to struggle with factual generation. So here are the results. We benchmark multiple proprietary and open-weight models on FactBench and measure their factuality or factual precision as the proportion of supported units. We observe that the model's factuality drops from easy to hard prompts, which is in line with our benchmark creation goal. Also, GPT-4o achieves the highest factual precision among proprietary models, and Mistral Large 2 among the open-weight ones. And interestingly, Mistral Large 2 shows surprisingly high factual precision, even outperforming all models in the easy category. So we also measured the factuality of these models using other factuality evaluation techniques that I will skip in the interest of time, but you can find more about them in our paper. Also, we keep updating our benchmark with new prompts and our leaderboard as new models become available. And you can find more about the performance of different models on our website. Another interesting finding is that factuality does not necessarily improve with scale. And as you can see, Llama 3.1405 billion instruct shows comparable or inferior factuality compared to its 70 billion counterpart as measured using different factuality evaluation techniques. So we found that Llama 3.1405 billion has the highest proportion of units labeled as undecidable. And this is due to the fact that the model generates more subjective statements, which contribute to the increase in the undecidable units. Here is an example that both 70 billion version and 405 billion version produce factual responses to a book recommendation request. As you can see here, the bigger version says that the book serves as a solid foundation. However, Verify labels this unit as undecidable, saying that there is no evidence to confirm its solidity. So in summary, in this chapter, I propose the factuality evaluation benchmark of real-world prompts that are divided across diverse topics, and the method for fine-grained factuality evaluation. Next, I will talk about inference time solutions to mitigate these hallucinations. But before, I can pause for quick questions. Okay, I can move.
I'll jump in with one. I find this very interesting. I was wondering if you could comment on the intuition that people have that bigger models hold more facts in the parameters and the results that you have. And maybe it might be a deeper question that maybe like the notion of factuality can kind of be subtle within that. But I just, it's a timely discussion. So that's why I was wondering if you have an idea.
Yeah. So for the factuality, how it's measured, it's usually like the standard metric is to first do some decomposition over, if we want to do fine-grained evaluation, which offers a more accurate evaluation, we can first do a decomposition of this very long text into several units, and then see how many of them are indeed correct. And this is a measure of the factuality. And so for the first question, can you please repeat that again?
Yeah, I'm just drawing on, I mean, I'm not an expert here, so I'm drawing on the intuition that people have said that bigger models like can store more facts in them, they have more parameters, and then when you're fine tuning them, they're like less likely to forget things or lose track of stuff.
Yeah.
And I'm trying to grapple this basic intuition that I have without having studied it with the results that you're presenting that says that it might be like it just might not be the case, or it's like more nuanced or something.
Yeah. So based on these results that I shared, so it depends on my understanding is that it depends on how these models have been also post-trained. So it apparently seems like this bigger version of Llama 3.1 produces more subjective statements, which is really difficult to verify. But the simpler and smaller version sticks to the facts and thus gets higher factuality score. But it's definitely understandable that as models get bigger in size, they can store more knowledge in their parameters, and so I think this is more of a post-processing style that this bigger model has been trained on to be more subjective and thus having a lower being penalized for factuality.
Yeah, that's a good point. I'll keep thinking about those things.
Yeah. Okay, so I can move to the next one. So as we saw before, different classes of techniques used to enhance the factuality of language models. There are these techniques that do not need a parameter, do not need us to update their parameters. In this chapter, we focus on model editing, or more specifically, activation editing methods, which provide direct control over language models to steer them towards factual generations. So research shows that these models know more than they say, and this is usually measured by the performance gap between the model's final generation and the results from the intermediate steps. So for example, when the model is asked, what's the capital city of Washington? The model's final generation might be incorrect, but an early exit from middle layers shows that the model has assigned the highest probability to the correct answer, which is Olympia, before shifting away from it in the final layers. Previous work also shows that these truth representations can be linearly decoded from the model's latent space. And since then, there has been multiple efforts in searching for these truthful directions and applying them to language models for factual generations. Inference time intervention, or ITI in short, is one example. It searches for truthful directions in the attention head activation space. So during ITI training, a question-answer pair where the answer can be either correct or incorrect is provided as the input. Then ITI trains linear probes on top of the attention head outputs to predict the correctness of these answers. Finally, truth-correlated probes are selected and their weights are extracted as truthful directions. And during generation, these weights are amplified by an intensity called alpha, and steered towards truthfulness. But there are limitations to these techniques. First is that this intervention intensity alpha is always fixed across all inputs. And second, steering a language model, if it does not know the correct answer, cannot lead to a factual response. So in this case, the model should learn to refuse answering. So I increased the intervention intensities to track the model's path to correct answer. And interestingly, the model, which is Llama 277B in this example, reaches the correct answer at different intensities depending on the input question. And also, as you can see in the last row of this table, it fails to reach the correct answer, which indicates the model's lack of knowledge. So these observations make me ask, can I learn these intervention intensities by analyzing the model's response, the evolution of model's response as the intensity increases? And also, how can I enable refusal when the model reaches its knowledge boundaries? So I designed an intervention framework that collects model responses at varying intensities, selects the most confident correct answer, and refuses to answer if none of the generations are correct. This framework, which we call LITO, has 3 steps, and I'll go through each step separately. So during the feature collection phase, for each input query, we first collect model responses at increasing intensities. So LM alpha is the language model that is intervened with the alpha intensity. And for each answer, we collect the average hidden representation of all of its tokens. Then we feed these collected hidden representations into LSTM to learn the sequential changes in response representations. And this is followed by a fully connected layer to predict the factuality label for each answer. And at inference, LITO selects the answer labeled factual with the highest confidence, that is shown here by the darkness of color. And if all predictions are 0, and so not correct, the LITO outperforms I have no comment to refuse from answering. And for evaluation, we measure the truthfulness accuracy score, where truthfulness is the proportion of accurate or uncertain responses. However, the model can refuse all the time to maximize its truthfulness, so we also consider the task-specific accuracy that can be exact match, for example. And here are the results with the original and ITI intervened language model shown in green and yellow. And also, we consider aggregation-based techniques such as majority voting, which selects the most repeated answer, maximum confidence, which selects the most confident one, and maximum confidence greater than some predefined threshold, which selects the most confident answer if its confidence is below a threshold and refuses to answer otherwise. And as you can see, LITO outperforms all other baselines with significant improvement on smaller models such as GPT-2 large and GPT-2 XL. And another interesting finding, which we can reach at by comparing the maximum confidence and maximum confidence greater than T accuracy scores, is that as these models increase in size, the confidence becomes more aligned with the accuracy. And in contrast, the smaller models suffer from poor calibration, as also supported by previous work. So in this chapter, I introduce a hallucination mitigation technique that adapts intervention intensity based on input context, enables refusal when uncertain, and is agnostic to the choice of the intervention method. So in this chapter, we went through the ITI instantiation of our framework, but you can find more about its effectiveness on other intervention techniques in our paper. Okay, so here's the end of chapter 2, and I can take quick questions before moving to the final chapter. Okay, I can move on. So next, I'll talk about a post hoc verification and correction technique for factuality enhancement. So we learned that manipulating a language model's latent space is an effective hallucination mitigation technique. But as I previously mentioned, language models have fundamental knowledge limitations. And there are retrieval augmented generation techniques that have been introduced to overcome these limitations, but these techniques still depend on the language model to generate responses. So we need post hoc validation techniques that can be used in complementary with other techniques and are able to attribute model generation responses to credible sources, detect errors, and make corrections. Here, I introduce our post-processing tool called Fleek, which works in 3 phases. In the first phase, The text is again extracted into triples, which are semi-structured formats we will cover later. Then the Flick will fact check triples against web articles and a knowledge graph, and provides attributions to correct claims as well as highlighting the incorrect ones. And finally, it makes corrections based on the retrieved results. So before getting into the details, let's first see a quick video of our tool. Okay. So first, the user input a response and hit the Ask LLM button, and then the model, which is GPT-3 in this case, generates a response. Then, by hitting the Start Checking button, the verification process begins. Here, we see two spans of text. One is questionable because based on evidence from knowledge graph, the Taylor Swift is not 30 years old. And another span is strongly supported, again, based on the evidence retrieved from the knowledge graph. And by hitting the Revise button, the questionable span will be corrected, and we have the correct generation. Also, Flick works by verifying any arbitrary piece of text. So here, if we put a piece of text and again check the Start Checking button, we can see that the model will produce and highlight multiple spans of text. One is strongly supported, two are highly likely supported, and one is questionable. And if we click on each span, we see the links that support the decision. And if we click on each of these links, we can go to the web page that the model relied on to make this decision. And finally, by hitting the Revise button, we can get the errors corrected. Okay, so here's what happens behind the scenes. Given a arbitrary piece of text, which can either be language model generated text, or it can be any text that the user wants to verify, Flick first extract triples from this text. And the triples are in the form of subject relation object triples. So here we can see one triple capturing the age information and another capturing the birth date. Finally, after that, Flick generates a query for each triple such that the objects of the triple is the answer to that query. So for example, for the triple, for the first triple, the query will be, how old is Taylor Swift? And then for each question, it retrieves evidence from using web search and a knowledge graph question answering system. And finally, it labels each triple based on the information retrieved. Triples that are supported based on the information from the knowledge graph are labeled strongly supported. And the ones that are supported based on web evidence are likely supported. And this is to accommodate for the less accurate evidence in the web. And otherwise, they are labeled as questionable. So also, there are clickable links, as you saw in the demo, to the web pages, and also evidence from the knowledge graph that will support Flick's decisions. And this will enable attribution and enhances our tool's transparency. And finally, it revises the input and corrects mistakes if they exist to improve the factuality of the response. And here are the results. To perform these tasks, Flick can be instantiated with any language model. And here we show Flick's performance with two instantiations, one with Vicuna 7 billion model and one with GPT-3. Initial experiments on Flick on a small-scale evaluation dataset demonstrates its reliability in factuality evaluation. And generally, GPT-3 instantiation outperforms the Vicuna one. Also, Flick successfully corrects 73% of hallucinations, which demonstrates its effectiveness in improving factual accuracy. Okay, so Here is the summary for the last chapter. I introduced the post hoc tool that can verify factual claims in language model outputs, attribute them to sources, and edits their hallucinations. This tool can be used as a complementary approach along with other factuality enhancement techniques. And here is a wrap of all the chapters. In the first chapter, we gain an understanding of the challenges in evaluating the factuality of language models. Then we adaptively intervened language model activations to mitigate hallucinations. And finally, we took an orthogonal approach to factuality improvement by performing post hoc verification and correction of model responses using external knowledge. Okay, so this is the end of all the chapters. My goal, my long-term research goal is to develop robust evaluation metrics that can measure language models' performance across different capabilities, and also methods that promote the truthful generation of these models. So, the evaluation provides a structured approach to uncover language model failures across specific targeted capabilities, such as reasoning, factuality, and instruction following. And to achieve this, we need to design an evaluation benchmark that measures the model's performance across diverse scenarios, and also a reliable method that can detect failures effectively. Currently, factuality is not a distinct area of focus in open language model evaluation frameworks, and knowledge recall benchmarks, such as those used for post-training evaluation in Tulu 3 recipe, provide some insights into factuality. However, they primarily assess the short-form question answering performance of different models using exact matching techniques. And these approaches have significant limitations when evaluating a model's factuality. One is that language models naturally generate long responses, and with techniques such as few-shot learning, we can make models to produce short responses and measure their knowledge, but these do not directly translate to the factuality of long-form responses. And also, prompting technique can affect the performance. And as you know, the choice of the few-shot prompting examples or the technique used can impact the model's accuracy, which can further introduce variability in the evaluation. So we need dedicated evaluation frameworks to assess the factuality of language models. And this is an area of research that I'm excited to contribute to in future. And second, many studies have shown that instruction fine-tuning or instruction tuning can hurt the language model's factuality. And here's how. First, introducing new knowledge can make the models overwrite or forget the information that they previously attained. And second, instruction fine-tuning can introduce new hallucinations. So consider this example where models pre-trained knowledge contradicts the instruction tuning data. So in this case, training on such an instruction tuning data set teaches the model to be inconsistent with its internal beliefs, a phenomenon also known as teaching it to lie. And to address these challenges, we need to target the factual consistency along with other capabilities, such as reasoning, during the post-training process. And to improve knowledge recallability, we can one approach that we can use is knowledge aggregation, which involves multiple representations of the same fact by using methods such as paraphrasing. And this technique has shown to be quite effective in enhancing the retrieval mechanism of language models during pre-training. And also, recent studies have shown that these aggregation techniques and fine-tuning on aggregation data sets can improve factuality recall during post-training as well. So how to design these benchmarks and how to design this and what part of the model to aggregate is one open question that I'm excited to contribute to. And also, alignment techniques can be used to enhance the knowledge recallability and the factuality of the model's response. And for example, reinforcement learning from verifiable rewards, or RVR, is a recent method for training the language model on tasks with verifiable outcomes, which means that this can be naturally extended to the factuality improvement problem, where the verification function can be a long-form factuality evaluation method. And finally, we need to teach models about their knowledge boundaries. So for the previous example, where the model's knowledge conflicts with the ground truth labels, the model should be trained to refuse rather than being trained on contradictory knowledge. But this will raise many questions, like how to create these data sets for uncertainty ever training. Should we also modify existing instruction tuning data sets so that they reflect the knowledge boundary of language models? And what techniques should we use to understand these boundaries? And these are all open questions that I am eager to explore and contribute to in my research. Thank you for your attention, and I'm now ready to take questions. Thank you.
Mm-hmm.
So I have one question here. Great talk. So your proposal on building a factuality related, kind of factuality driven benchmark to evaluate all these like post-train models. How are you, like, can you dig a little bit deeper into that? How are you proposing one can do that?
So by generally looking at what are the targeted capabilities that these models are being evaluated, for factuality, it seems like these models are vaguely evaluated on the knowledge recall tasks, as mentioned in the Tulu 3 paper. And these are, first, the knowledge is also, the benchmarks also stale, like, again, at the risk of data leakage. And also these are only measuring the short form question answering performance of these models. So, but we know that these models naturally generate long answers. So how to evaluate them in their natural setting? And one thing that can be done in the first place is to use the factuality evaluation benchmark that I proposed in the first chapter to get a sense of what are the different failure modes of different models, different open language models that are used in AI2, and then get insights and move forward. But also one thing that I saw was that there is no, also that I also mentioned, there is no training on the model's knowledge boundaries, and this is one thing that I think is seriously missing and can really contribute to a larger set of hallucinations. So the model can even hallucinate more than its pre-training phase, because if the fine-tuning data is in conflict with the pre-training data, then there would be hallucinations. And I saw that there are benchmarks that like other models may use to do this knowledge boundary training, but I couldn't find it in the recipes in the OLMO team.
Quick question, following up this. So I'm assuming like this is something similar to refusal training where where you like basically anything that is out of the pre-trained knowledge, you try to refuse that, right?
Yeah. Yes, that's the case, and I think that's one thing that can significantly impact the factuality.
Any other questions for Farima today? Looks like no questions. So let's thank Farima for her time today, and Farima, have a good conversation with the rest of the team today.
Thank you so much.
Thank you.
Okay.
Thank you all.
Thanks, everyone.
Thank you for attending.
Bye.